So in the continuation of the last lecture, dear students, now I would like to tell you about the differential and integral form of Faraday's law, which too has a great importance in physics. Many students think that it is simply a mathematical manipulation, but I would like to tell you that the differential form or integral form of the Faraday's law is defined as one of the Maxwell's equations in electromagnetism, and the Maxwell equations I will tell you in the upcoming days in the relevant chapter. You will see that the importance which Newton's laws of motion holds in mechanics, the Maxwell equations in electromagnetism are having the same importance. Before going to the actual mathematics of this particular topic, I would like to mention some interesting part that many students every year asks me, sir, what is the difference between closed path and closed surface? Dear students, there is a very simple way to learn it. You just see a bangle, you just see a circle, you just see a rectangle, a triangle. These are two-dimensional closed geometries. Two-dimensional closed path, so that defines a closed circuit. Any geometry which is two-dimensional and it is in the form of any closed curve, then it is called a closed path. What is the beauty about closed path is, suppose this is a closed path, and I take the example of a cube. A closed path always surrounds a certain area, surface area. Every closed path surrounds a certain area, encloses, you can say, and closed surface always encloses certain volume. So wherever you see that there is a three-dimensional structure, three-dimensional geometry enclosing a certain volume, then you can define a closed surface for it. And whenever there is a closed path, it is a two-dimensional geometry, then it will enclose certain surface area, you can say. It will never enclose any sort of volume. Be careful. You know, when I defined the change in flux in the very beginning of this chapter, then I talked of a closed path. So Faraday's law was E equals to minus d phi by dt. There is no need for any sort of argument now. You know it. Rate of change of flux. What is this phi? Look, phi is the magnetic flux which is passing through this surface which is enclosed by the closed path. Listen it again. Here phi is the magnetic flux which is passing, which is defined for the surface which is enclosed by the closed path. So phi is nothing but integration of p dot ds defined over the whole surface S of the, so this is surface S through which the magnetic field lines are passing. I hope you can understand it very easily, right? This is second equation. Now we know by the definition of EMF or electromotive force or potential difference that it is simply the work done by the electric field. So I can say if induced electric field is E vector, then what is E? E will be simply integration of E dot dl over the closed path. E is the induced electric field. Now I put these values for E as well as for phi in the first equation using first and second and third equation. In first I shall get, I'm writing it here, I shall get integration E dot dl over the closed path is equal to minus integration of dB by dt ds. This is what I'm going to get. Or it can be written as minus d upon dt b dot ds This is called the integral form of Faraday's law. It correlates the induced electric field with the time varying magnetic field. Remember, here dB by dt means the magnetic field surely is changing with time associated with the closed circuit, closed path. And hence we are correlating it with the induced electric field. I would like to share a very, very, very important concept here, that this induced electric field is a non-conservative electric field. Many of you don't know because you start from the first chapter of electrostatics at your starting physics level and you begin to think that electric field is always a conservative field. But I would like to tell you, dear students, the electric field which is induced in the phenomena of electromagnetic induction is always non-conservative field. And I had the opportunity to observe this effect in the early 2004 when I went to Jodhpur University, and some of great professor like Professor Majumdar sir was able to demonstrate this particular phenomena, that electric field is a non-conservative field, using a standard experiment. It is tough for me to explain that particular experiment because a long solenoid was used and some resistances were used, closed circuits were used, but I would like to tell you that I have seen it, and that's why I can say that this electric field is a non-conservative electric field in the phenomena of EMI. Now, dear students, you can use the Stokes-Curl theorem, and Stokes-Curl theorem, all of you are familiar that it can be written as E dot dl equals to minus curl of E I hope in the first chapter book you have gone through all these rules. So using Stokes theorem, I can write down curl of E is equal to minus delta B upon delta T. This is the differential form of Faraday's law. So hopefully you enjoyed today's lecture. In the next lecture I will tell you about the self-induction, and I will calculate it for various circuits. Using the Stokes theorem I got it, the differential form of